I'm going to talk about a specific application of the technologies that you just heard about. So, my particular field of interest is in studying the brain injury in children who've had prenatal alcohol exposure. And the umbrella term for this set of disorders is fetal alcohol spectrum disorder. There we go. So this is what I mean by I don't really do much. These are the people that I've been able to work with over the course of many years. So as Vic said, my training is as a basic biomedical scientist. I trained in pharmacology and toxicology. Never did I ever once, for the first 10 or 12 years of my career, believe that I would ever be involved in clinical research. It's not my field. I'm not trained in it. But one day I sort of woke up to the fact that all of the information, as Steve was talking about one of these values of depth, all the information that we were generating in basic biomedical studies in this field had little impact on clinical practice because there was no way to get them from the lab to targeted studies in kids where they were actually needed. So it was a chance conversation with Doug that got me involved in iMovie studies in this population. It was a chance conversation with somebody who said, I should go talk to Steve about robotics and how that could be useful. So I've been able to collaborate with these two individuals over the last several years with some very exciting results. So, why should we care? Well, prenatal alcohol exposure actually turns out to be the leading preventable cause of development of brain injury. And this is a global problem. There's estimates that somewhere between 1% to 2% of Canadian children are affected by this disorder. And there are a number of countries in the world where that percentage is much, much higher. So this is a global pandemic that is affecting large numbers of children throughout their entire lives. But it's a very complex disorder. It's not a single thing. Prenatal alcohol exposure can induce a large spectrum of brain injury in kids. It's going to vary. It's different from child to child. And that's going to be because of differences in timing and extent of exposure, genetic predisposition, nutrition in the mother, nutrition in the child postnatally. And it can lead to a large number of deficits in executive functions, learning and memory, social communication skills, attention, and sensory motor processing. A lot of the things you've been hearing about over the last several minutes. So clinical assessment of a child with a history of prenatal alcohol exposure is pretty complex. FASD is an umbrella term for a number of disorders that can occur in kids. And these are the three major ones. Fetal alcohol syndrome, which was the first recognized disorder in this group. But we now know that there's a thing called partial fetal alcohol syndrome. They have some of the presenting features. And the real big problem is alcohol-related neurobehavioral disorder. Now, the diagnosis of ARD is a significant clinical problem because the physical features, the facial dysmorphology, the growth restriction that occurs in kids with FAS and partial FAS is not there. They look perfectly normal. And it's actually about 80 to 85% of the affected children are in this group. They have no physical presenting features. They have a brain injury. We can't see the brain. What we see is a child with behavioral problems. And so they get labeled as a child with behavioral problems. But in fact, what they have is a brain injury that's the cause. And as I say, there's a whole bunch of different phenotypes that occur in this group. So the presenting features of one child are not going to be the same as the next. So this presents very, very significant clinical problems. What do we do with this population? Well, here's some of the problems that we have to deal with. So the battery of tests that are used in the diagnosis is quite extensive because we really don't know what domain of brain function to measure in any affected kids, any one affected child. FAC is a heterogeneous group of disorders, so it's not really clear if there's a single cognitive test that would be more sensitive or specific than any other. The diagnostic assessment involves a multidisciplinary team, almost always a physician, developmental pediatrician or a clinical geneticist, together with a psychologist, a speech-language pathologist, and a case manager. We got a whole bunch of people in here. Lots of highly paid health professionals that are necessary for each child. Each assessment takes up to 2 days. In fact, I was reading a recent assessment. It could be 24 to 30 hours of contact time for a single assessment. And it's fairly expensive. Our capacity for doing these diagnostic assessments in Canada, this is Canada-wide, is about 3,000 per year for all kids with a neurodevelopmental disorder. That includes autism, ADHD, FASD, and all the other ones that you could think of. So our capacity is very limited. And in large clinics, only about 60 to 70% of the kids who are actually referred for a diagnosis leave with a diagnosis of an FASD. So we need to do something better. Hence these gentlemen. So what I've done through collaborating with them is to try to exploit these emerging technologies to develop these assessment tools and apply them in this clinical population. There's a real downstream payoff for this because the earlier and more accurate identification of a child with a neurobehavioral disorder leads to earlier interventions, longer term, better outcomes long term, less cost. Less cost in the healthcare system, less cost in the educational system, less cost in the judicial system, which is where most of my kids end up, and so on and so on. Increasing long-term employability and income in this population. There's huge economic benefits that can be measured from the accurate application of these tools. So we've done a few studies. I'm going to give you just a taste of a couple of things we've done with the KinArm and with iBalloons. So I'm not going to tell you anything new that you haven't already heard. I'm going to tell you about a specific clinical application and where it can take us. So we started a collaboration with Steve 6 or 7 years ago now, I think. We did a small pilot study in a group of kids with FASD compared to controls. And the data looked so good that Steve's company actually scaled down the robot to a kid-sized version called the Kid KinArm, which would fit these younger and younger kids. So we could bring in 5, 6, 7-year-old kids to do these types of assessments. And they really loved the robot. I have not met a kid yet who did not love playing in the robot. So here's, again, something Steve showed you, some of the outcome measures that we can take from this. A simple reaching movement from some starting point to a target. And a couple of things that are really key is this first one, this error, this direction error. You know, every time you make a motor movement, you reach for a glass of water, you reach to pick up your car keys. You make that movement, and it starts off very inaccurate. But your brain is monitoring and providing feedback and correcting that movement even as it's going on. So that by the time you get to the end of it, you've reached the glass and not missed it, hit the table. So that feedback, correcting the motor movement, we can get an index of what's happening by looking at what's this direction error. And then by the end of the first movement, how far are they away from the target? That is, how efficient was that first motor movement when they had to execute towards a target? Well, again, here's some visual data. These are data from 2 kids, a 14-year-old control participant over here, and here is a 14-year-old child with an FASD. I actually had ARD. I was there when this particular child came in. You can't tell by looking at it that he has developmental disability. But a few minutes in the KinArm, and visually, you don't even have to analyze this. Visually, you can tell something's wrong. And so we look at a number of these outcome measures in the kids. Here's some data from the 2 groups. And so here's this, these 2 parameters I talked about. Over here is the direction error. And so here's the control kids. You know, they're a nice tight group. They're all very good. They're all getting pretty close to the target. The direction there is not large. The distance from the target, not too bad. Then we look at the kids with FASD, and they have a large error. And they're way off the target by the time they make that first movement. And I gave you these things don't mean much to you, but to a clinician they would mean a lot. This effect size is a measure of how far apart the performance of the two groups is. And it's clinically important because any effect size that's actually larger than 0.8 is considered to be very large and clinically significant. And here, with a couple of simple tasks, we get effect sizes that are enormous and are very clinically significant, showing us the impairment in the motor process in these kids. And that, again, is going to affect their everyday activities, what they're capable of. Why do they have problems with games? Why are they not as good athletically as their peers? Well, it's because their brain is not working optimally. It's not providing them that feedback to improve or correct their motor processing. Here's the ball hit test. They love this. They love hitting things. You know, what kid doesn't like hitting things? And just as Steve showed you, these balls come down and they hit them. Well, the kids with FASD make more errors. They miss more targets than do the control kids by a fair amount. And we try to ask, why do they do this? Why are they making these misses? And what came out is this we call the hand box. And this is the propensity of the individual to use their dominant hand, the one that they have best control over to hit more targets. And in the controls, they have this bias towards using their dominant hand to hit more targets. Whereas kids with FASD have almost no bias at all between their hands. Now, there could be a lot of explanations for this, but one of them that actually I thought of recently I'd like to pursue is this idea that we might actually pay more visual attention to what our dominant hand is doing because it is more efficient. And if these kids are not, then that is going to have a significant impact on their motor abilities. This is something that could be trained. This is something that intervention strategies could be designed for to improve function. But we have to understand what the deficit is before we can actually intervene with what's going to be an effective program. Okay, so I'm going to switch over now to some of the stuff with eye. And again, go back to this idea. When a child is referred for a diagnostic assessment in Child Development Center or any other behavioral clinic, they're going to have a huge number of tests. Hours and hours and hours of tests in all of these different domains. Sensory motor, social perception, visual spatial processing, memory and learning, language, attention, and executive functions. Because we don't know what to test, so we test for everything. Hours and hours and hours and hours. I would not personally want to go through this. It's incredibly boring for the kids. And it's expensive. So here's one of these tests. This is a clinically used test in the assessment of child cognition. It's called the animal sorting test. And what the kids are asked to do is to take a group of 8 cards that have different pictures on them. And without instructions, to use internal strategies to sort these cards into groups. Whatever they want to do. So you can see some of them in this simple example. Some of the cards have 2 animals and some only have 1. So there would be a sorting strategy that could be used. And they use as many as they can think of, self-generated strategies to sort these cards. And we just measure how many, what their progress is through this test. I'm only going to show you the one. But we did a study with a large number of kids, and we took a partial battery. This is a small selection of the tests that would be used in the clinic. We looked at their performance in all of the outcome measures that come from these tests. And you get a lot of outcome measures in the different tests. But we also looked at eye movements. We do the ProSACAD and ASACAD tests that Doug talked about in this population, and they had a lot of problems with it. I'm going to talk about that one as much as this idea of this natural viewing, watching movies. And you've already seen this. When you watch a movie, your eyes are going to all the salient features in this movie all the time. Hundreds and hundreds of times, if not thousands, of these saccades, these behaviors that we captured over a short period of time. And there's no instruction. Just watch the movies. So here's an example. This is good. Or not. Here's an example of the kind of movie clips that we'd show. They're semantically unrelated. You have no idea what's coming next. They change quickly. As Doug mentioned, our attention wanders very quickly when we're looking at the same thing. So we need to change the scene very, very quickly. That re-engages attention circuits, and our eyes follow the salient features. Again, kids will watch movies for long periods of time, but we actually don't need long periods of time to collect a lot of data. 10 minutes of watching these video clips is sufficient. So again, collaborating with some really smart people, not me, at the University of Southern California, take all of the information that we've gathered. I didn't talk about imaging, but we have a lot of neuroimaging data on these kids as well. And we have all of these neuropsychological outcome measures. And we have their behavior when they're watching movies. We put this all into a model and let a computer essentially pick the features, the outcome measures, out of all the things we've collected. What are the things that distinguish these two groups? It was actually kind of surprising. So we got down to the end of it, classification scheme, using, I'm just going to talk about the bottom, the very end. The features that the computer model selected were two of our psychometric tests, 2 out of the 20 some outcome measures, and the behavior of kids watching these movies. Captured, accurately classified over 90% of the kids with an FASD. Separated them from controls. The specificity, the sensitivity of the test was 96%. It's huge in the clinical world. It takes less than 30 minutes to do this versus the 30 hours of clinic time to get to the same answer. So this is where we're going with these technologies, applying them now prospectively in clinical situations to compare how these tools compare to the current standard of care in the clinic, and can we actually streamline the diagnostic process? Can we develop high throughput, low cost applications that would accurately and with great sensitivity identify children with a developmental brain injury? It's also gaining this insight into which brain cognitive functions are most effective. In my case, with prenatal alcohol exposure, but we can apply these same tools in other neurodevelopmental disorders as well. We can streamline the screening and referral process by identifying these children who do have evidence of brain injury, who would most benefit from the diagnostic assessment. And again, just as the case for all other disorders, it's the early identification. The younger we can push this back, 3, 2, 3, 1-year-olds, actually doing a study with infants, 1-year-olds will watch movies long enough for us to collect information about their brain. It's that early identification that puts those kids back onto a trajectory for meeting developmental milestones and for mitigating the long-term health educational outcomes associated